Hey everybody, today I'm going to do a video that's pretty different from my usual content. This video is aimed at the treeple out there. That's more for the industry that I'm in now as opposed to the abstract mathematics that I usually make videos about. Another title for this video could be, how hard do things hit the ground? Or in our case, how hard do you hit your saddle when you fall? And in general, what this video is going to be talking about is the impact force on a falling object as a function of the distance fallen. So if you know how far something falls, what is the impact that it feels when it stops? So prerequisites for this video to make any sense, you need to have done high school physics. Hopefully that's fresh in your head. So here we go. So the first things we're going to assume, and you don't have to worry about this too much, is that the force of impact is constant and the force of impact is in the same direction as falling. I have it in quotations because it really, you're falling down and the impact is up, but those are in the same line. If that doesn't mean too much to you, don't worry about it too much. That's more for the people who are more mathematically and physically inclined. So we need those assumptions to give us this equation. And this equation says that the work done on a system, and I'll talk about what that means in a second, is equal to the force on that system times, that's what that dot is, the distance that that object feels this force. In this case, the work is the energy gained by falling. What is the work? It's the energy that is given to the object you care about in the circumstance you care about. So in this case, you're falling, so you're gaining energy as you fall, and there's no energy being given to something when it's in free fall other than the energy it's getting from gravity, i.e. falling. Over here we have the force of impact. That's the thing we're looking for, so that's cool. And then it's being multiplied by the distance of stopping. So once something is falling, let's say I'm in my harness and I'm falling, and from the moment the rope starts to catch me to the moment I come to a complete stop, there's some distance traveled there. Like my rope stretches a little bit as the saddle catches me. Like you don't just instantaneously stop. And what I want to point out here is that this is not the distance fallen. This is the distance that you cover while you stop. Okay, so if we divide both sides by d, because I want the force of impact, so if I divide both sides by d, it cancels out here. We get the force by itself, which is what we want. The impact force, which is the thing we're looking for, is the work, or the energy gained while we fall, divided by the distance it takes us to stop. What the hell is the work? How much energy do we gain while we fall? Okay, reiterating what I said before, recall that the work is the energy gained by the object of study, the thing we care about, me or the piece of wood that you're rigging, whatever, which is the energy gained by falling. So also, recall that when an object falls by a distance, I'm going to call h. This is the distance that you fall now. That's what h is. The energy gained by falling due to gravity is given by this following equation. So the energy that gravity gives you, right, energy gained by falling, is equal to the mass of the object falling, g. This is just a number, but it's kind of a funky number, so instead of writing that number out every time, we just gave it a name, because it comes up over and over. But that number is 9.81 meters per second squared. We don't have to worry about that. We're never actually going to use it today in this video. But if you want to understand what's going on, or maybe you have some more background, that's what that is. And again, like I was saying earlier, here's h. This is the height that you fall. So the work is all the energy you gain while the circumstance you care about happens. So is there any other energy being given to you while you're in free fall other than from gravity? No, it's just the energy that you gain from gravity. There's nothing else to add here. So the work, the energy I gain, is just the energy I get from gravity, which we found the equation for that is m times g times h. I didn't write the dots. If there's no symbol in between the letters, it means you multiply them. Just a little reminder. So if we plug that into the equation that we had before, remember, we had that the force of impact is the work divided by the distance it takes to stop. Well, we know that the work is mgh. So here we have a new formula for the force of impact. Recall that the force of gravity is given by this equation. The force of gravity is equal to mass times this number 9.81, which we have written as g. And this is what is often called weight. Like when someone says the word weight just in casual English, they're talking about the force of gravity on that object. When you stand on a scale and the scale gives you a number, it's measuring how hard gravity is pushing you into that scale. So I'm going to call mg w. For weight, I'm just going to give it a new name. The force of impact was equal to mg times h over d. Well, mg is weight. And this is just a little bit of algebra. So if the object's in free fall, when the impact occurs, free fall just means there's no forces acting on you other than gravity. This is the total force, often called the net force, is going to be equal to the force of gravity, right here, plus the force of the impact. Now, I am doing a little bit of hand waving here, but if you know enough about physics to ask questions about this, then you know enough about physics to figure out the answer to what's going on. I'll leave that as an exercise for the viewer, but it has to do with the fact that when we're stopping, we're not in an inertial reference frame. Since the force of gravity is being referred to as weight, so let's call Fg by W for weight. Then we have here that the total force is equal to the force of gravity, well that's just the weight, and then the impact force, well we found that that's the weight times the height that you fall divided by the distance it takes for you to stop. We can pull that W out, right? Whoop. And then here I factored the W out. So that ends the discussion of the force that you feel, that something feels on an impact. After this next section, the discussion moves specifically to arboriculture. So this is in general the force that something feels when it falls, if you know its weight, how far it falls, and the distance it travels while it stops. So it's commonly assumed in my industry that the distance to stop due to our climbing systems is 1 foot. So D, the distance it takes to stop, is 1 foot. And if we measure the height, I should say H, the distance that we fall, if we measure that in feet, then when we look at this fraction, here, it ends up being just the number of feet that you fall. Just a number, not a length anymore, just a number. So I'm going to call that number H. What does that mean? Let me give you an example. So suppose you fall 6 feet. That means H is 6 feet. Then H over D, well that's 6 feet. We're assuming that D is 1 foot. The feet cancel out. The units go away and we're just left with the number 6. So N is 6. And we can rewrite our equation like this. The force that you feel when you hit the ground or your system catches you is equal to your weight times the number of feet you fall plus 1. And I've sometimes seen it written like this, that the force you feel is your weight times the number of feet you fall plus your weight again. Now the most important thing to realize that when we're using this equation, we're assuming it takes 1 foot for you to come to a stop. From when you start slowing down to when you hit a speed of 0, distance that you travel while you're stopping is 1 foot. And that's really all there is to it. I just have one more page that I'll throw up where it's just going through the math. If you just want to sort of cut to the punchline without any of these explanations along for the ride, then this is what you get. So the amount of math that we're doing here is not a lot, but because we're looking at physical examples, it takes a little bit more explanation to see what's going on. But I mean, this is the entire calculation here. We're not using anything fancy. It's just high school algebra and high school physics. So if you're familiar with that, I'm really hoping that you were able to follow along with this and you get a little bit more understanding as to what's going on in this formula that, at least for me, in my industry, I've used and talked with my coworkers about a whole bunch of times. I hope that this provides some extra context and you got something out of this video. Stay safe, everybody, and I'm probably gonna make some more of these tree videos, so maybe I'll see you in the future. Don't worry, I didn't forget about all you people who live in sane countries. So I came up with a metric version for this as well. Now I'm assuming a slightly smaller stopping distance, like D, the distance it takes to stop. But that's okay because you get a greater force, which means you're assuming the worst case scenario. If you're using this formula, the actual force you feel, if you stopped in 1 foot, this force you calculate here will be greater. So you're still safe, but regardless, this formula is true if you assume a stopping distance of 25 centimeters. So in this case, you take your weight and you multiply it by not 1 plus the number of feet, it's 1 plus 4 times the number of meters. So you have this extra step where you multiply the meters by 4. So that's what this is saying. Nm is the number of meters. So it's really similar to the imperial version. About the same amount of brain power required to use, and it works for all our friends in places that use metric instead of imperial, because we're kind of crazy over here. Awesome, thanks for watching, see you next time.